Okay, today we will cover 11.3, the integral test, and if possible, we touch base a little bit on 11.4, the comparison test. Okay, now integral test, it will be done in the following way. So suppose you have a sequence that is decreasing, and when I plot the sequence, let's say it looks like this. So this is for n equals to 1, n equals to 2, n equals to 3, n equals to 4, and on. I think I draw too much of this, but okay then. Now, to find the sum, of this sequence, we will add the following area of boxes. You know what? I will just use this. I'll just do it this way. So I create a box here. Okay. Now the area under this box will be the sum up to the nth term. Okay, so this is the first term. The area of this equals to the first term. The area of this is the second term. Okay, so the sum, the second partial sum will be the total area of the one I shaded here. Okay, let me go back. Erase this, otherwise there will be too crowded. So you will see that if I want to add those sequence, I'm basically finding the area of all these rectangles added together here. Okay. Now, compared to, so I go on right now and fx be the superposition function. Fx itself, I think I should say superposition continuous function. Where the fx is decreasing on the interval 1 to infinity. Okay, now because fx is the continuous superposition function, it means right at 1, 2, 3, 4, and on, the graph of fx should hit those numbers, those coordinates. You see what I mean? Now, notice that because the function is decreasing, oops, because the function is decreasing, then notice that the area, the total area of those boxes is greater than the area under the curve from 1. Observe that the integral from 1 to infinity of that function is less than, at most equal to, the sum, infinite sum of the infinite sequence, right? You see that? Why? Because if you look at that rectangle, we always have extra stuff. You see that? We always have extra stuff because it's decreasing, right? Because it's decreasing, then the sum, the series will be more than the integral. Is it right? Okay, and of course the error here gets smaller and smaller. Now that's the first observation. Okay, now also suppose I draw the boxes differently. Suppose I draw the boxes differently. This time I want to use, let me use green color. Suppose I draw the box differently. So let me ignore the first term. Let me ignore the first term. I start from the second term. So A2, the height is here. A3 is height here. A4 is height here. A5, the height is here, and so on and so forth. Now this is a graph that is becoming so complicated, such that if you don't follow me since the beginning, you may be lost to what I'm doing. Now, so you see that this is the area of that represent the second term, right? This is the area that represent the second term. That's the height of A2, right? This is the area that represent the third term. The area represent the fourth term, the fifth term, the sixth term, seventh term, and on. And notice that this blue shaded region always below the curve. Do you notice that? Okay, so the second thing we see here is that the area under the curve of that fx is always greater than the summation of the sequence from 2. You see that? Not from 1. Not from 1. Now, in other words, then, you see that if the integral is convergent, then for sure the summation from the second term to infinity is convergent. Is it right? And moreover, adding the first term into that series from the second term adding the first term into the series of the second term, which is the infinite sum from the first term, is also convergent. Okay, you just add one term, it will not change the convergence, right? Of course, with the assumption that the first term is finite, okay? So from here, we draw a conclusion. If the integral is convergent, then the summation is convergent. Agree? Oh, you know what? I have one more thing I need to say. Decreasing non-negative sequence. Non-negative sequence, sorry. Non-negative. To be more positive, precise, it has to be positive actually. Well, anyway. Now, on the other hand, you see that if the series is convergent, then of course the integral is convergent. Is it okay? You see that observation? Now that brings us to that integral test. So we have this integral test that says that suppose fx is continuous, positive, decreasing. Function on 1 to infinity. And the sequence is equals to Fn. Then the integral 1 to infinity of fx dx and maybe I say it this way. The integral from 1 to infinity of fx dx is convergent if and only if the infinite series is convergent. Okay, now that is the integral test. That is the integral test. Okay, the integral and the series will have the same convergence. But please note that, okay, we do not say that the integral is equal to the series. No, that's not what we say. Okay. The integral may give you a number that is different from the infinite series. Okay. They may not converge to the same number. They may not converge to the same number. What we know is they just have the same convergence. Both of them convergence or both of them divergence. Okay. We just say both are convergence or both are divergence. Okay, that's one. Second, the requirement, the decreasing requirement in fact, not only the decreasing requirement, the positive requirement is not necessarily start from 1. how to say it? I think my grammar is not correct. The decreasing requirement is not necessarily started from 1. Is it the or does not necessarily starts from 1? Yeah, it doesn't have to be, it does not need to start from 1. Maybe, yeah, let me say that way. It does not need to start from 1. We just need the function and therefore the sequence to be eventually decreasing. Okay, so here's the idea. Here's the idea. So your curve, your graph may look like this. Okay, now the first couple terms may not really follow, will not satisfy the integral testing, right? Okay, but the first couple terms does not decide. The first couple terms does not decide if the sequence, if the series is convergent or divergent. Okay, as long as it is eventually decreasing, then eventually this theorem or this test applies. Does it make sense? Okay, so there's a capital N here. There is an N such that fx is decreasing for x greater equals to that capital N. Okay. So we can, we don't need to be super strict on the fact that the function has to be decreasing from x equals to 1. No, it doesn't have to. Okay. Also, it doesn't have to be strictly positive at the beginning, as long as eventually decreasing, eventually positive, then it's okay. Now, but the continuity we cannot sacrifice though. Okay, maybe to be more precise, we don't need the function fx for the first couple terms. Okay, we just need the continuous positive decreasing function, decreasing superposition function on some n to infinity. That's what we need. Okay, now, so here's the thing. Later on, when we apply this test, we need to find the continuous superposition function and show that first it's continuous, give the reason why it's continuous. Okay. Second, that it is decreasing. One way to show is to show that the first derivative is negative, or you show that term by term. Okay, and of course show that it is non-negative. Now let's start. Too small. That one is too small. Okay, let's say I pick questions from number 5. You know what? Give me a second. Give me a second. Okay, I will pause my recording. Okay, let's see number 5. So test whether yeah, it will come back as soon as I start again. Test whether the series is convergent or divergent. See, it comes again. The series is convergent or divergent. And the series is, maybe I call that the question. And then for number 5, we have this series. One over 2n plus 1 cube. Solution. Now I will make it 2 columns, okay, here, so that you know better how the storyline. Okay, so I will start with let fx equals to 1 over 2x plus 1 cube. Note that fn equals to 1 over 2n plus 1 cube, which is equals to the sequence. That's to show that this is a superposition function. Now, we need to show a couple of things. We need to show that this function is continuous, okay, but why? Fx, so maybe I write it this way. So claim Fx is continuous on 1 to infinity. Proof. Proof. Fx is a rational function with domain all real numbers except -1/2, right? Okay, and from a theorem we have in calculus 1, if it is a rational function with domain blah, then that function also continues on that same domain. Consequently, then we can say the function is continuous on what we need, 1 to infinity. Second, claim the function is non-negative. And again, what you need is from 1 to infinity, or to be more precise, is from some capital N to infinity. Proof. N starts from, for x greater than 1, for x greater than 1, then 2x plus 1 will be greater equals to 3, which is greater than 1, which is greater than 0, right? Strictly greater than 0. Okay, so 1 over 2x plus 1 cube, therefore, must be greater than 0. Once an expression is positive, then the reciprocal is positive. Right? So fx is positive on, maybe I use equal sign here, 1 to infinity. claim fx is decreasing on 1 to infinity. Now, later on in your test 4, to be more precise, okay, the fact that the function is positive, you can just say, obviously, it's positive. Just make sure that it is really that obvious. Okay, what you don't want to say, obviously, is positive on that 1 to infinity, and it turns out that it's not true. Okay, continuity, you need to argue. Maybe you need to argue in words the way I did. But the fact that it is decreasing, that's something you need to prove hard in a way that we don't skip the proof for decreasingness. Okay, the fact that it is monotonic decreasing is something you need to show explicitly. Okay, and one way to do that is, let me show you the first way. You do the derivative fx equals to 1 over 2x plus 1 cubed. So this is, the derivative will be negative 3 2x plus 1 to the power of negative 4 times 2. That's equals to negative 6 over 2x plus 1 to the 4. Okay, now, and this is negative because 2x plus 1 to the 4 is always positive, correct? In fact, it's always positive for any x. So the function fx, the function fx is decreasing. The function fx is decreasing at least from x equals to 1 to infinity. Okay, so you set up the stage first. So this function is not only the superposition function, but that superposition function is continuous, positive, and decreasing, right? You see that we will spend a lot more time in showing those 3 key ingredients. Now the integral from 1 to infinity of 1 over 2x plus 1 cubed dx is equal to what? That's limit at t goes to infinity, integral from 1 to t, 1 over 2x plus 1 cubed dx. That's why we learned this first, right? In the previous sections. Chapter what? Chapter 8 maybe? Okay, and then we do u substitution. So du is 2 dx, right? So limit t goes to infinity of, this is 3, this is 2t plus 1. And we will get, this is u to the power of negative 3 du over 2. Okay, and then you integrate this. This is 1/2 limit t goes to infinity of negative 1/2 u to the power of negative 4. Hold on. What am I doing? Negative 1. No, negative 2, not negative 4. From 3 to 2t plus 1. That is negative 1/4. Limit t goes to infinity of 1 over u squared from 3 to 2t plus 1 So this will be 1 over 36. Now notice that what I did here, I actually compute that integral and show that it converges to a number. And that's actually not necessary. That's actually not necessary. Why? Because all I need to show is this integral is convergent. We don't need to find the actual value because after all, the value of this integral, the value is in this integral is not the same to the value of the summation. Right? No, they are not the same. So we don't need to show what's the value of that integral. We just need to show the convergence. Okay, so what happened here, I overkill it. Nothing wrong with that though, you know. Nothing wrong with that. Okay, but then you claim by integral test, then the series, make sure you be explicit which series you're talking about. Okay. How would you have done without showing the value? We can do comparison tests. Let me show you here. Okay, so the alternative way, so let me do it. Let me cancel this boundary here. Do the alternative way. Okay. Now, integral from 1 to infinity of 1 over 2x plus 1 cube dx is less than equals to integral from 1 to infinity of 1 over 2x cubed dx. Is it right? Okay, which is equals to 1 over 8 integral from 1 to infinity of 1 over x cubed dx, which is convergent by p integral p equals to 3. Is it right? Okay. So we can just conclude right away then by integral test. And from there, we go here. Okay. Now, that reminds me that I need to talk about p-series. In my video, I believe I already explains that p-series is the integral of 1 over n to the p, which we prove by integration. We prove by integration that this p-series is convergent for p greater than 1. It has to be strictly greater than 1, and divergent for p less than equals to 1. Okay, see the proof. See the proof in our textbook or my lecture. Okay. Now we say this is p-series if it's 1 over n to the p and the sum is from 1 to infinity. Okay. Now, how do I use this for question number 5? You may be surprised. Okay, go back to number 5. This sum, infinite sum from 1 to infinity of 1 over 2n plus 3, oh, I'm sorry, plus 1 cube. This is less than equals to this. Is it right? Can I say so? Okay, 2n is less than 2n plus 1. Right? So 2n cube is less than 2n plus 1 cube. Okay, but these are positive terms such that the reciprocal is still positive. Is it right? But this is equal to 1/8 of the infinite series. Okay, but this series here is a p-series with, let me just say what p equals to, with p equals to 3. So this integral, I'm sorry, this series is convergent. Is it right? And if you have non-negative series bounded above by something convergent, then you will see in the next section, we call that comparison test. But you know that intuitively, if you have a non-negative series, bounded above by something convergent series, then that series must be convergent. Okay? Now, this is something we later learn in this is in 11.4. Okay? Do you have any question you want me to pick? Besides this number 5, of course. Take a look on page 745. Page 745. Take a look which question you want me to go over. Between number 9 to number 26. Somehow I think integral tests and comparison tests supposed to be taught in the same section. Otherwise, then there will be some, it's hard, we need to do it a hard way. For example, number 26. Number 26, let me say I go over this. This is the series from 1 to infinity of n over n to the 4 plus 1. Now we know this is less than, to be safe, less than equals to n over n to the 4th, right? If I divide by smaller number, then the quotient will be larger. But this series is the same to 1 over n cubed, which is convergent by p series p equals to 3. Okay? Does it make sense? And this term here is always positive, not negative, right? For n greater or equals to 1. In other words, it is bounded below by 0, and that series is positive series. So you keep on adding positive number and bound it above. Okay. So if I just use comparison test, so by comparison test, which you will learn in the next section, this series here is convergent. Okay, now here's the thing, but what if we don't do it by comparison test? We use integral test instead. Then we will be busy, right? See how busy we will be? Okay, how we will do it? If we do so, let fx be x over x to the 4 plus 1. Okay, and what else? Note that fn is n over n to the 4 plus 1, which is a sub n. Okay, then fx is continuous on all real numbers. Okay, well, I will just say note that fx is continuous on all real numbers. Okay, and positive. Fx is greater than 0 for x greater equals to 1. Right? Okay, when x is positive, the numerator is positive, denominator also positive. Claim, the one I need to show, that the fx is decreasing, at least eventually. Okay, so proof f prime x equals to the denominator x to the 4 plus 1 squared. The numerator will be x to the 4 plus 1 minus x times 3x cubed. I'm sorry, 4x cubed. That is 1 minus 3x to the 4th over x to the 4 plus 1 squared. Now this will be negative when 1 minus 3x to the 4th is negative. Okay, when x is greater than 4th root of 1/3. For sure, it works for x greater equals to 1. This is just to show that this x is the suitable functions that we look for, the superposition, decreasing, continuous, positive functions. Now then, now we do the integral. Integral from 1 to infinity of x over x to the 4 plus 1 dx. First, we take care the infinite domain, right? Limit t goes to infinity of integral 1 to t of x over x squared x to the 4 plus 1. Now you tell me what to do from here. This is what happens if you don't learn comparison theorem first. Any idea how to integrate this? I will use u equals to x squared, such that the du will be 2x dx. Okay, limit t goes to infinity of 1 to t squared. Okay, this is 1 over u squared plus 1 du over 2, right? So that's equals to 1/2 limit t goes to infinity of tangent inverse u from 0 to t squared, from 1 to t squared. That's limit t goes to infinity of tangent inverse t squared minus tangent inverse 1. But you see, if you do integration, you really need to compute that, right? Unless you actually want to go on from here, that this is actually less than equals to integral from 1 to infinity of x over x to the 4th. You see what I mean? You get p series. I'm sorry, not p series, p integral. P equals to 3. You see what I mean? Okay, now that way, you don't need to do integration, like really actually find the value of that integral. But once I actually go this direction, then I have to compute it. This is pi over 2 minus pi over 4. With the boom, that's pi over 8. Then you say by integral test, the series is convergent. Okay. So that's the idea for integral tests. Now, I want to go on further to do the estimate. Let's look back here. Let's look back here. Notice that the integral from 1 to infinity, is bounded above by the sum from 1 and bounded below by the sum from 2. You see that? Okay. Now, if you think about that argument, notice that using the theory, we have the sum from n equals to 2 to infinity of a sub n is the lower bound of integral from 1 to infinity of the continuous superposition function and bounded above by the infinite series from the first term. Okay, now I can change this integral here, let's say from k to infinity instead of from 1, and it is bounded above by the infinite sum from k and bounded below by infinite sum from k plus 1. You see that? Oh, Thomas, why do we need that? I want to do it this way. Okay, suppose we consider the summation from n equals to 1 to infinity. This infinite series here is separated by the sum up to k, maybe k minus 1 to be more precise, plus the sum from k's term to infinity. Maybe use this one here. I use k here, and this is k plus 1. So this series is actually bounded above by the kth partial sum and the integral from k to infinity. You see, I use this one here. Okay, so we can say the following. The actual sum, we usually call that just S, minus the kth partial sum is bounded above by integral from k to infinity of fx dx. Is it right? So that's one. Basically, if you want to squeeze the error is bounded above by the integral from k to infinity of fx dx. The error of the first k term. If you add up to k, then the maximum, the error is equal to that integral from k to infinity. Okay, now let's try to do number 37. Part A, use the sum of the first and 10 terms, in short, find as 10, to estimate the infinite series from 1 to infinity of 1 over n squared. How good is the estimate? Okay, so what we will do is solution. The first part, what is S10? S10 is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, all the way to 1 over 10 squared. Okay, let me use my Excel to do that. Oh, hold on, I don't have Excel on this computer anymore. Give me a second. What should I do? Spreadsheet. Hold on, I didn't see that we have my explanation of estimate is not in the original YouTube video. Oh yeah? Okay, maybe I was rushing that I didn't go that far. I didn't. Oh, I remember that. I didn't explain it, but I did a problem. I think I did number 36 there. Yeah, I think I did number 36 there. Give me a second. I want to use Excel to help me visualizing the estimate. Give me a second. I want to use spreadsheet blank. Okay. This one here. Maybe let me enlarge that. Okay. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is equals to 1 over that thing squared. And I will copy that. Okay, so the sum of the first 10 terms will be this guy. Okay, that's the sum of the first 10 terms. 1 point, you know what? I'm lazy. Let me screenshot that. And go back to our here and we say this is equal to this. Okay. Now the thing is, how good is that estimate? Can we find the error? So the second part of that is the error. The error of the first 10 terms will be at most integral from 10 to infinity of 1 over x squared dx. You see what I mean? Okay, which will be limit t goes to infinity of 10 to t x to the negative 2 dx. Gada bam, gada boom. That will be 1/10. Okay, so the error will be at most, the error is at most 0.1. Okay. So if the question is how many terms should we take such that the error is less than 0.01, and you see here you need to set, maybe I call that another question. How many terms to get error less than 0.005. So basically you need to find k, need k such that this error here is less than equals to integral from k to infinity of 1 over x squared dx, and you set this less than 0.005. Okay, that push the error to be less than, even less than the integral, which is less than 0.005. But according to our computation here, we get this is 1 over k. Is it right? From our computation above. Okay, so the reciprocal k must be greater than 1 over 0.005. 200. You use 201 then, because we want less than, right? Now, we have another technique to improve our estimate such that you see that you don't need 200 terms to be that accurate. Actually, no, you don't need 200 terms. Let's take a look on part B. Part B. Improve this estimate by, that's box 3. That's a technique they describe in our textbook with n equals to 10. Now, before I show you this technique, let me go back to my explanation up here. Something I tried to explain earlier, but I don't want to go too deep such that we don't even know the foundation. Now, notice that if I break it this way, then the sum of the first k terms, the kth partial sum, has error at most this. But I would also like you to realize that at the same time, the summation from k plus 1 to infinity of a sub n, this is greater equals to something. This is greater than integral from k plus 1 to infinity of fx dx. In other words, if I squeeze that here, okay, the sum from 1 to k of a sub n plus the sum from k plus 1 to infinity of a sub n, this infinite series here, is bounded below by the sum of the k term, integral k plus 1 to infinity fx dx, and bounded below by the kth partial sum plus integral from k to infinity. Okay, so the kth partial sum, this is our kth partial sum here, okay, has error at most this, at least this. Imagine if I subtract f sub k. So going back to that theory, okay, the infinite sum, we can write this as the sum from 1 to k plus from k plus 1 to infinity, that's bounded above by the k partial sum plus integral from k. And bounded below by the kth partial sum plus the integral from k plus 1. Okay, this is our kth partial sum, right? This is our kth partial sum. This is our kth partial sum. This is the infinite sum. So you see that if I subtract by kth partial sum, then the error is bounded below by integral from 1 to k plus 1 to infinity, and bounded above by integral from k to infinity. Okay, in other words, if I go back to this question, in this question, the 10th partial sum, which was this, okay, has error bounded above by integral from 10 to infinity of fx dx, yet bounded below by integral from 11 to infinity of fx dx. Okay, we computed earlier, then the error will be at most 1/10, at least 1/11. In other words, therefore, the infinite sum, which is the 10th partial sum plus the error of the first 10 terms, will be bounded below by this guy plus 1/11, and bounded below by this guy plus 1/10. So the infinite sum will be at most 1.649767731, but at least what is 1/11? 1/11, that's 1 plus 549767731 plus 0.090909091. That's 1.6406766822. You see how accurate we are? We are accurate to third decimal place. So our infinite sum must be located, yeah, it's 0.091 if you want to round it to 3 decimal places. Okay, so if I want to improve my estimate, I know it must be between this guy and this guy. Then let's estimate it this way. Let's call this as the midpoint of those two numbers. Make it in the middle. Pictorially, it is between 1.6407 and 1.64998, right? Okay, so this is where the infinite sum is supposed to be. Now, if you want to improve your accuracy, get the midpoint here. So instead of taking so many terms, you take only 10 terms. You take only 10 terms, and you achieve a very, very good accuracy by doing this procedure here. Okay, 1.6407 plus 1.6498 divided by 2. This is 1.64525. And notice that my error, by doing the midpoint of this, my error will be less than that now. My error is already at most 0.00455. In other words, if you see what I had here in the one I did in red, using the original technique we had earlier, okay, using original technique we had earlier, how many terms do we need to get accuracy such that the error is less than 0.005? And it says that we need 200 terms, at least 200 terms, right? But if you improve your computation this way, you only do 10 terms, right? But your integral from 10 to infinity, integral from 11 to infinity, okay? And then you take the midpoint, right? Your error suddenly guaranteed even less than if you take 200 terms. Remember? See, if I use 200 terms, my error is less than 0.005, right? Okay, but actually, no, you don't need 200 terms as long as you combine it. Okay, as long as you combine it. Okay. They say that they have the exact value in number 34. You know what? I don't know what's the exact value, and it doesn't matter. Let me do this thing. I go back here. Okay. But let's see what is the sum up to, let's say, the 30th term. The good thing with Excel is you can visualize that. So the sum up to the 10th term will be this. Okay, that's the sum up to the 10th term. Now I will go on further. Oh, you know what? I'm sorry. Yeah, I need to go this first. How many terms do you want? 36 terms, 37 terms? Okay, then let's see what happened to the 37th term. How close are we? Let me screenshot this. If we go to the 37th term, that's what we get. I'm sorry, that's way too big. Make it smaller then. Now let's use our calculator. I need to get that. That's It's basically 1.549767731 plus the average of 1/10 and 1/11. So according to my computation here, if I use the sum, this 1.645222276, this error here, this estimate here, has error less than 0.00455. Okay, now the sum up to the 37th term is this. That's the sum up to the 37th term. Okay, the sum up to the 37th term, that is 1.618269, let's say, has error less than 1/37, but the error must be more than 1/38. Okay. Let's go back to this thing here. I wonder if I go on infinite of like very, very far. Let me go. I'm about to give you a break. How far do I want to go? Let's say 151. Did I make any miscomputation? I feel like it's supposed to be 1.638 something. 1.638 something. How about my computation here? Let me go back. What I'm afraid is I make miscomputation, that's all. We know the sum should be less than this. We know the sum should be less than this, and has to be greater than this. The sum has to be, yeah. So I don't go far enough, huh, to even, oh, how to say it? See, this is not even 1.64 yet. This is not even 1.64 yet. How far do I need to go to make it 1.64, huh? Okay, let me stop here for now. Pause. From number 34, the exact value for this infinite sum is this number here. That's the exact value. Okay, so if you compute the difference between this number and that number, it's actually less than 0.005. 4 already. Right? Yeah, it's quite accurate. Now, I try to compute the sum up to 261 terms. Don't worry, I didn't actually do it by hand. I use Excel. Okay, so suppose from my Excel, we get this number here. Okay, the sum up to 261 is 1.64110,998. Now, the error for 261st up to 261 terms is at most 1 over 261, but at least 1 over 262. That's the error. Okay. That's the error. So what is the difference there? If I take the midpoint of this error, I set the error to be that, I will get the error will be 0.03841. So I will improve my estimate by adding this number. 1.64110,998 plus 0.00, I miss one extra zero here. 0.003841. And the better estimate will be 1.644934. Okay. In other words, if you add only up to 261 and you stop there, your error is still pretty far, right? Your error is still pretty far, 0.004 something, 0.003 something. Okay. Now, but when you do the error analysis, get the midpoint of the upper and lower bound of the error, and you add that to this number, right? Notice that you are now accurate to 6 decimal places. Okay, this is accurate to 6 decimal places. Actually, I can say accurate to 7 decimal places. Basically, you can do variation after you get the sum, and you do variation. Now, let's apply this technique a bit to number 38, which is a question that I thought I did in my lecture. Number 38. Okay, find the sum of the series correct to 3 decimal places. Okay, I will just do the standard way first. I will do the standard way first. So I need my error to be less than 0.001. And to avoid the error, I mean the rounding error, to accommodate rounding error, we use E, we set the E to be half of that. How about that? Okay. Now then, we find K such that integral K to infinity of 1 over x to the 5th dx is less than 0.0005, which I think is 1 over 2000. Anyway, we integrate this. Let's just do it pretty fast. This will be what? -1/4. So it'll be 1 over 4x to the 4th. K, actually, 1 over 4k to the 4th. That is less than 1 over 2000. In other words, 2000 is less than 4k to the 4th. Divide by 4 and take the 4th root. K equals to, I think when k equals to 5 is good enough, huh? K equals to 5, k to the 4th is already 625, right? Okay, so we just need 4 terms, actually. I mean, 5 terms. Let's do so. Let's do so. Okay, so k is at least equals to 5. Okay, now let's actually find the first 4 terms, 5 terms, as 5 equals to 1 over 1 to the 5th plus 1 over 2 to the 5th up to 1 over 5 to the 5th. Let me just use my calculator. I get 1.03666 17. You know what? Let me make it 7 here. Oh yeah, that's right. 6662 then. Okay, and we know the error up to the 5th term will be less than equals to 1 over 4 times 5 to the 4th, but greater than 1 over 4 times 6 to the 4th. You see that? Okay, let's take the midpoint of that. We approximate that using 1/4 of 1 over 5 to the 4th plus 1 over 6 to the 4th divided by 2. I do the midpoint, which is 1/8 of that's actually a very small number, 0.00237716. 1/8 of that will be 0.00029645. So we will use this estimate instead. 1.036662 plus 0.000296. I will use this number instead, and this is very accurate. This is very, very accurate. The error is already, the error from this, so using these numbers here, the error is already less than 0.000296. Hold on. No. Less than 5 to the 4 times 4, do the reciprocal. The error is less than 0.0004. Okay, but the error here is even way smaller. This is notation to say that it's very, very smaller, much smaller than 0.0004. Okay, now let's see. Use my Excel. Where's my Excel again? Hold on, let me call my Excel. I actually uninstall my Microsoft Office. Don't be bored with me, please. So I have 1, 2, 3. Let's go to how many terms? Maybe up to 20 terms. Okay, and this is equal to 1 over, this is 1 over this to the 5th. And this is equals to this guy, but this guy will be let's see what happened. So the first 20th term we are already here. Okay, so the first 5 terms, the sum of the first 5 terms, and modifying that, I get so close to even if I go 20 terms. Okay, see 1.03693 for that. You see? Oh, hold on. That's supposed to be 6 decimal places. Let me see my calculator. Why I only write 5? That's 5/8 supposed to be. This is 5/8. Okay, so it's pretty close already, right? So what I want to say is this: if you actually do up to 20 terms, this is the number you get, but you can get this number only going up to 5 terms and error analysis. Okay, let me spend a little bit more time here. I hope you can understand what I do with my Excel. If you are in computer science, actually, you can understand this better. Okay, this is what I want to do. This is what I want to do. Insert something here. Okay, this is my n. This is my nth term, right? This is the sum up to nth term. What I will do next is the error up to nth term here, upper bound. Upper bound for the error of the nth term, which when we compute earlier, it should be equals to 1/4 times the nth to the 4th. The error up to the nth term lower bound is 1/4 times that n plus 1 to the power of 4. Now the mean of the error, error of the nth term will be this guy plus this guy divided by 2. Okay, so this is improved sum of n, which is this guy plus this guy. So this will be the estimate up to the sum up to the 20th term. This is the sum up to the nth term after we improve with error analysis. Okay. So if I go to the, let's say I go to the 10th term only, this is the sum up to 10th term, but together with error analysis, I will get this. Okay, notice that my 10th term compared to the actual 10th term, if I go to that, the 10th term here, okay, the difference between this guy and that guy is less than, like this is already the 6th decimal place. So you go to 20 terms, I go only to 10 terms our error is so small. Let's see. Let's guess if I go to only 5 terms with the improved result compared to if you go to 20 terms without improving the result. Let me screenshot that and put it in there. Oops, sorry. Into my note. Make it a bit smaller. This is my Excel result using number 38. Okay, this is the error between if you add 20th term up to 20 term and the modified S5. The modified S5 is this compared to if you go to 20 terms. This is the error between, this is error between S20 and modified S10. That's 0.0000203.662. Okay, so you can imagine how close is this one. Right? So modified sum for the first 20 terms. So not just the sum of the 20 terms, but I modified that also. Okay. This has errors to the actual sum that must be less than 0.0000001. We are accurate to at least 7 decimal places. Why? Because even up to the sum of 10, it's already accurate to 6 decimal place, right? So this one must be very, very small. Okay. That's the benefit of doing that modification. Okay. Sorry if I sounds like I'm working on my own outside of textbook. I just try to show you that the theory, according to the theory, okay, you take 5 terms, you add the first 5 terms, you are accurate to, we are already accurate to 3 decimal places, right? But if you modify that, okay, you are actually accurate to a lot less than that 4 decimal place. Okay, a lot accurate to that 4 decimal place. Okay, that's how good our modification be. This is much, much less than. Much, much less than. 1636958 Yeah, that's, I don't even know what is the actual sum though, to be honest with you. I don't know what is the actual sum. Okay, I want to move to 11.4. I go to 11.4. It consists of two parts. First one, the one that we easily understand, the comparison test. That basically says the following. Of course, I only have half an hour, right? 20 minutes actually. So I won't be able to finish this section. No rushing. I'm not rushing. The comparison test says the following. Let the series A sub n and the series B sub n are series with positive terms. Okay, now if part A, if, maybe I do it this way instead, sorry, and A sub n is less than B sub n for all n. Now, consequently, of course, if you have that term by term, Bn is greater than A sub n, then the infinite sum will be also like this, right? Is it right? Okay, now. So first, if infinite sum of Bn is convergent, then that infinite sum of Bn is the upper bound, convergent, then A sub n is also convergent. But if the lower bound is divergent, then the series Bn will be divergent. So if you can find a series that is bounded above by another series that is convergent, then that series is convergent. So idea, if this, you have these terms is bounded by Bn and the sum of Bn is convergent, then the sum of A sub n is convergent. Okay. However, if your series Cn is bounded below by Bn and the series Bn is divergent, then your original series is divergent. Okay, let's do problem now. Example, let's see number 3. The series determine whether the series is convergent or divergent. Number 3, the series from 1 to infinity of n over 2n cubed plus 1. Okay, solution. N over 2n cubed plus 1 is clearly less than n over 2n cubed, right? Does it make sense? Well, because maybe we say it this way first then. 2n cubed is less than 2n cubed plus 1. Is it right? That's always true. That's always true. Okay, and that's positive. Yeah, you need to make sure it's positive because if one of them negative, the reciprocal may not be true. Okay, maybe not true. Okay, but then if I do the reciprocal now, then 1 over 2n cubed must be greater than 1 over 2n cubed plus 1, right? And if you multiply by a positive number n, if you multiply by a positive number n, the inequality is maintained, right? But then you will see, so this series here is bounded above by this series, which is equals to 1/2 the series 1 over n squared. Since the series 1 over n squared is convergent by what? You need to give the argument why that is convergent. Don't just say, oh, it's convergent. Why? You know, it's convergent. It's convergent by P series P equals to 2, right? Then, by comparison test, the series n over 2n cubed plus 1 is convergent. Okay, so you see that I actually do using 2 tools here. First, I use comparison tests. First, I use p-series test, p equals to 2, p-series, to show that the upper bound is convergent. Therefore, the actual series that we are dealing with is also convergent because it's bounded above by something convergent. Number 7. How about the series from 1 to infinity of 9 to the n over 3 plus 10 to the n? Solution. Yeah, of course, that 9 to the n over 3 plus 10 to the n is always positive and less than 9 to the n over 10 to the n. Right? Okay, so that series is bounded above by another series but that series happens to be a geometric series. Okay, now but This series, the last series, that's why we need to be explicit, is a geometric series with r equals to 0.9. The magnitude of r is less than 1. So this series is convergent. Okay, and by convergent the comparison theorem, the original series that we are dealing with is also convergent. How about number 9? Yeah, number 9. The series of ln k over k. Okay, now ln k is greater than 1 for k at least 3, right? Yeah. ln 3 is greater than 1. ln e is equal to 1, right? Okay. Since ln e is equal to 1, then once the argument is greater than e, starting from 3, then ln k is already greater than 1. Okay. Now then ln k, therefore, over k is greater than 1 over k. For k greater equals to 3. Is that right? So the sum from k equals to 3, not from 1 to infinity of ln k over k is greater than the sum from k equals to 3 to infinity of 1 over k. But that series k equals to 3 to infinity 1 over k is convergent, divergent. It's divergent. Why? Because that series is harmonic. Right? Okay. So that series, could P series also be a reason? Yeah, you can. You say that it's because 1 over k, the series of 1 over k is P series P equals to 1. Yes, you can. So k from 3 to infinity of ln k over k is divergent. Okay. But that's the term from 3, right? What happened with the term from 1? Yeah, you add 2 terms, the first 2 terms, it doesn't change the result. It will still be divergent. Okay, so using comparison theorem becomes a lot faster. Okay, a couple more questions. Do you want to choose some problem maybe? Oh, number 17 is interesting. How about the series from 1 to infinity of 1 over square root of n squared plus 1? Now, why this question is interesting? Why this question is interesting? Let's take a look first. Let's take a look at why this question is interesting. Because of the following. You may think that you want to bound it above by 1 over square root of n squared, which is 1 over n, right? You can bound it above that way. But the thing is this. The thing is this. If you bound it above by something divergent, this is divergent, by the way. Okay. It does not mean this is divergent. No. If you want to bound it above, you have to bound it above by something convergent to say that the original series is convergent. You cannot bound it above by something divergent and say this is divergent. No. No. You know that 1 over n squared is less than 1 over n, right? Okay. Such that the series also bounded above. But this is divergent. We know this is convergent. Okay, so you cannot bound it above by something divergent. Okay, if you want to show that it is this, if you want to show that this is divergent, if you want to show that is divergent, you need to bound it below by something divergent. Okay, okay. Now the purpose of this question for number 17, actually, they want you to use limit comparison theorem. Okay, only if you follow my lecture live, then you will hear this. Our textbook wants you to use limit comparison theorem. What is limit comparison theorem? Now, limit comparison theorem, which I will discuss on Thursday, or I'm sorry, on Monday. Limit comparison theorem says the following. Okay, if so, let the series A sub n and series B sub n are series with positive terms, and the limit n goes to infinity of A sub n over B sub n is a positive constant. Okay, C is finite, positive and finite. Then these two series are both convergent or both divergence. Very similar to integral tests. Okay, now that's what they want you to do. That's what they want you to do. Let me show you first what they want, and then I will show you my way in which I don't use limit comparison theorem. Okay, so basically let A sub n be 1 over square root of n squared plus 1. That's the series. That's the terms that we originally have in that series. Consider B sub n equals to 1 over n. Even though 1 over n is larger, the bn is larger than A sub n, but when n is very, very large, they behave quite similarly. Okay, they behave quite similarly. Now, limit comparison theorem works for the situation where they behave similarly when n goes to infinity. Okay, so limit n goes to infinity of a sub n over b sub n equals to limit n goes to infinity of 1 over square root of n squared plus 1 over 1 over n. That is limit n goes to infinity of n over square root of n squared plus 1. Divide the top and the bottom by n. I don't think you want to do L'Hopital rule because after all, it's not continuous. Okay, and it's actually harder to do. Now this is finite and positive. Okay, now since 1 over a, the series of Bn, which is the series of 1 over n, is divergent by harmonic, then by limit comparison theorem, the series of an, which is 1 over square root of n squared plus 1 is also divergent. Okay, that's what our textbook wants you to do. You may think that's shorter, but consider the following way. This is, you can call this Thomas way, but no, this is not Thomas way. This is just try to play, massage the situation. Alternatively, notice that the series 1 over square root of n squared plus 1, this series here, I do it this way. N is greater than 1, right? Okay, that's actually from the indexing. So I can do n squared is greater equals to 1. Is it right? N squared plus n squared is greater equals to n squared plus 1. Does it make sense? Okay, such that the square root is greater equals to the square root. But then the reciprocal, you reverse the inequality sign. Right? And of course, we maintain that's positive. So the series here is less than equals to the series here, less than equals to the series that we want to observe. But the series on the left-hand side is actually one over n square root of 2, right? Which is equal to 1 over square root of 2 of the series, our harmonic series. Yeah, time's up, so I want to finish this fast. The series 1 over n is divergent by harmonic. So by comparison theorem, the series which any series greater than that must be divergent. Okay. In other words, I actually use this property here. If you want to bound it above, you can bound it above by square root of n squared. Okay, you get rid of this. But if you want to be bound it below, I'm sorry, it's the other way around. You bound it below by that, but you bound it above by this. Right? Such that when you take a look on the reciprocal, you see that? Okay, that's actually the play I did. Now, a lot of students I saw, they like to use limit comparison theorem, but actually no need, no need. Okay, that's for today. Let me finish here and see you on Monday. On Saturday, remember, at 8 o'clock, I will go over some tests. But before I forget, I hope you are still listening to me. Let me do this. Let me do this. The discussion. Did I post the old test that I want to go over? Yeah. Yeah, I post those two tests. Let me take a look if I have the solution. Okay, let me take a look if I have the solution. Now try to do them on your own first before you look at the solution, okay? So go back to that discussion on 2 days ago. From fall 20, I will give you the solution here.
And that's going to be recorded on Saturday, right?
On Saturday, yeah.
Okay.
Fall 20.
I think I'll be able to attend it.
And then, but what I plan to do on Saturday is this. I hope that you already start working on these all tests, such that on Saturday, you just ask me question. Thomas, you know what? I look at your solution, fall 20, test 3, solution number 5. I don't understand it. Can you explain it? You see what I mean? So you already have the solution here. You already have the solutions here. Study from those, and then if there's anything that's not clear, then you can ask me a question. You see what I mean? Okay, but in general, I'm happier with your test compared to your first test. Your first test was quite disaster. But your second test, I have, I think I have one person, 3 people get more than 70, actually almost 80. Almost 80. You know, it's learning process. I hope your test 3 gets even better. Okay, this is from April the 26th. We are on April the 28th, but if you want to get the solution of those tests, those 2 tests, then go back 2 days ago. Okay, then that's for today. See you on Saturday, maybe otherwise Monday. See you.